On to lecture 15. Triple integrals in cylindrical coordinates, and I should have added and also spherical coordinates. So we're looking at triple integrals in both cylindrical, and then later on we will look at them in spherical coordinates. So just like there are some double integrals that would be easier to evaluate if they were written in polar coordinates, there are some triple integrals that would be easier to evaluate if they were in cylindrical coordinates or spherical coordinates. Now you see cylindrical coordinates, what should come to you is a cylinder, and a cylinder in 3 dimensions has a formula x squared plus y squared equals a constant. So therefore what should come to you is polar. Alright? So in polar coordinates and double integrals are the same as cylindrical coordinates and triple integrals. Spherical coordinates, we're looking at spheres. Okay? So let's start with cylindrical coordinates. So first of all, as I said, cylindrical coordinates is similar to polar coordinates, same formula, but we are in 3D. So again, you're going to use these formulas. X equals r cosine theta, y equals r sine theta, and z is just going to be z. You leave it as z, and you use x squared plus y squared equals r squared. Alright? So the first thing we're going to do is convert points in rectangular coordinates, points in cylindrical coordinates to rectangular coordinates. And to do this, we are going to use this formula above there. Okay, now in cylindrical coordinates, this is the point. This here, the first coordinate is r, the second coordinate is theta, and the third coordinate is z. Okay, so if I go from rectangular to cylindrical coordinates, I am going from x, y, z to r, theta, z. Okay? Right, so let us use these to find the rectangular coordinates for that point. So we need to find x and y. So we're going to use the formulas above there. X equals r cosine theta. So here, x is equal to 6 cosine pi over 3, which when you look at that in your calculator, that is 3. And y is 6 sine pi over 3, which is 6 times root 3 over 2, which is equal to 3 square root 3. And so your rectangular coordinates for this point would be the x, the y, and the z, which remains as -2. Okay, let's do the other way now. We now want to convert from rectangular to cylindrical. So basically it's the same thing you used to do when you used to convert to polar. So the z remains as 1, but these you need to convert to r and theta. So here x is -1, y is 1. Okay? So let's find r. That's the first thing we need to find, r, and then we find theta. Okay? The r is easier. So r, remember, is the square root of x squared plus y squared. So it's 1 plus 1, which is square root 2. Now to find theta, if you can remember your unit circle, but if you can't, that is okay, because you can just work it out. So the point -1, 1 is here. Oops. Try again. You need this angle. All right, what angle is that? 3 pi over 4, right? So theta is 3 pi over 4. And so in cylindrical coordinates, your point is square root 2, 3 pi over 4, and the z coordinate remains as 1. Okay? Okay, why don't you try 2 on your own? Convert to cylindrical, just as we did, and then to rectangular. Sorry, convert to rectangular first, and then to cylindrical. What am I saying? I'm saying something. I have the wrong point here. There's an error here. I'm so sorry about that. 2 4 pi over 3 8. This should be convert to cylindrical. This is wrong. This point should be square root 3 1 4. Okay? All right. So rectangular first and then cylindrical. Okay, let's go over it. Rectangular coordinates, so use your x equals r cosine theta and so on. So x equals 2 cosine 4 pi over 3. What did you get here? -1, great. Y equals 2 sine 4 pi over 3. What did you get? Negative square root 3. Good. And so your point is -1, negative square root 3, and 8. Okay, now the other one, you need to find r. What did you get for r? 2, good. So r equals the square root of square root 3 squared, which is 3, plus 1 squared 1. So that gives you 2. Now let's find theta. So if you draw this is square root 3 and this is 1. So you're looking at this point. And this is the angle. What angle did you get for that? Pi over 6. Good. And so your point is 2 pi over 6, 4. Okay, so I just wanted to do a couple of examples with you showing how you convert. All right? But let's go on to the real stuff now. Any questions on that before we move on?
If you do the tan inverse of 1 over square root of 3, you get pi over 6.
Yes.
Okay.
Mm-hmm. Tan inverse of 1 over square root 3 is pi over 6. Okay, let's move on. So what are we learning to do now? We're learning how to convert triple integrals to cylindrical coordinates. And again, what do you look for if you are not told? The same thing you looked for when you were doing polar coordinates, right? You need to see it's over something circular, or maybe you might see something with x squared plus y squared, right? So a triple integral can be converted to cylindrical coordinates as follows. So it yields, so you just change the x, y, and z integrand to something in r, theta, and z. But always remember you multiply by r, the Jacobian, okay? So it's the same thing. Let's do some examples. We're just converting. Convert the integral to an integral in cylindrical coordinates. Okay, so if you're converting, I want to see r limits, I want to see theta limits, and I want to see the z limits. Let's start with the r and theta because that is something that you are used to. So to do the r and theta limits, we are going to concentrate on the dx and the dy part. So the r and theta, you put it in 2D. All right, so you project it into 2D. Now, first of all, we need to draw this. What does this look like? All right, so let's make a drawing. You have y going from -2 to 2, right? So you know that the curve must pass through these two. And then you have x going from negative square root of 4 minus y squared to square root of 4 minus y squared. What type of region is that? It's a circle. It's an entire circle, right? So we're going to do okay. So if we are looking at an entire circle, can you give me the limits for r? 0 to 2 pi. Can you give me the limits for theta? Now, sorry, this is I'm sorry. I mixed it up, right? R is what? 0 to 2. Oops. And theta is 0 to 2 pi. Now let's find the z limits. So we're looking at the innermost integral. That's z, so the innermost integral says that z goes from square root of x squared plus y squared to z equals 2, right? What is the square root of x squared plus y squared? R. Good. Square root of r squared, which is r. So therefore z goes from r to 2. Okay? Now let's convert. All right, integral. Let's convert the integrand first. The integrand is xz. What is x in cylindrical coordinates? R cosine theta times z, right? What else do we need? The Jacobian, which is r. And we put dz, dr, d theta. And so your limits go from r to 2, dr 0 to 2, d theta 0 to 2 pi. Okay, and you can simplify this to 0 to 2 pi, 0 to 2, r to 2, r squared cosine theta, let me say r squared z, cosine theta dz, dr, d theta. So that's the first one we have just converted, okay? Any questions? Next. Now this one we're going to convert and also evaluate it, okay? Just so that we can get some practice. So I'll put here evaluate also. Okay. So let's start. Again, start with your r and theta limits. So the r and theta limits, you look at the first two integrals, okay? And then you always draw. It's always good to draw a picture, all right? So the outermost integral, if you notice, it corresponds to dx. So x goes from -1 to 1. And the y goes from 0 to square root 1 minus x squared. What are we looking for here? Half a circle above the x-axis. That's what we want. Give me the limits for r, please. 0 to 1. Give me the limits for theta, please. 0 to pi. Good. Okay. Now let's get the z limits. From the innermost integral, z goes from 0 to y, right? So that means z goes from 0 to r sine theta. Very good, because y is r sine theta. Good. Any questions so far? Because we are going to set up now. Okay, let's set it up. So the integral becomes, let's do the integrand first. X squared is what? R squared cosine squared theta. What else do we need? Jacobian r. So this becomes r cubed and then we have dz dr d theta, z 0 to r sine theta, r 0 to 1, theta 0 to 2 pi.
Just pi.
Pi, thanks. Okay, now we want to integrate, okay? So let's do this. The first thing we integrate with respect to z. So this becomes r cubed cosine squared theta times z from 0 to r sine theta. Well, this is z equals 0 to r sine theta dr d theta. Let's substitute r sine theta for z. This is equal to 0 to pi, 0 to 1. This becomes, when you substitute r sine theta, you get r to the 4th cosine squared theta sine theta dr d theta. Now, let's integrate with respect to r. So 0 to pi, this becomes r to the 5th over 5 cosine squared theta sine theta from r equals 0 to 1 d theta. Substitute, you will get 0 to pi. When you put the 1, that's 1/5. I'm going to put it outside the integral. And so inside you have cosine squared theta sine theta d theta. What technique do we use? Substitution. What is u? Cosine. U equals cosine theta. Du is minus sine theta d theta. So sine theta d theta is minus du. Change the limits. Theta is 0, means that u is 1. Theta is pi, means that u is negative 1. And so this converts to 1/5 times the integral from, and make sure you put the limits in the correct order, 1 to negative 1 of u, or minus, so let me put that minus outside, minus u squared du integrate minus 1/5 times u cubed over 3 from 1 to minus 1, which is minus 1/5 times, put minus 1, you get negative 1/3, minus, put 1, 1/3, which ends up being 2 over 15. Any questions here? Okay. Is it your turn? Do it then. So this one, I just want you to convert, okay? Just convert, you don't have to evaluate. Okay, so let's go over this. So you use these two integrals to draw your diagram so you can find the r and theta limits. So x goes from -3 to 3. Based on the y limits, just like the last one, we are looking at above here. And so r goes from 0 to 3, and theta goes from 0 to pi. Z goes from 0 to 9 minus x squared minus y squared. So here, z is 9 minus r squared. And so to set up, the integrand is square root of r squared, which is r. Jacobian, multiply. So you have r squared dz dr d theta. Z goes from 0 to 9 minus r squared. R goes from 0 to 3 and 0 to pi. Please always remember the Jacobian, because if you forget, that is a crucial error and you lose a lot of points. Okay, it's important to put in the Jacobian. Do you have any questions on this? Okay, let's move on. So let's look at some applications whereby you have a problem and you want to, again, I am not going to tell you to use cylindrical coordinates, but based on the type of problem you should know, okay? Let's look at number 1. Find the volume of the solid above the xy plane bounded by the paraboloid z equals x squared plus y squared and the cylinder x squared plus y squared equals a squared. So you see the presence of these x squared plus y squared should tell you you are going to use cylindrical coordinates, okay? Alright, so let's set up the integral for volume in triple integration. Now, by the way, also note this question can also be worked in double integration. All your triple integration questions can be worked using double integration. Just know that, alright? But we're in triple integration, so let's do it. So in triple integration, remember volume is equal to the triple integral of 1. Remember that? Okay, now as I said, we are going to use cylindrical coordinates. Now if you look at the cylinder, they actually told you gave you the equation of the cylinder. That should give you your r and your theta limits. So let's go to the cylinder. So x squared plus y squared equals a squared. Let's convert this. In converting this, what do we have? Anybody can tell me? R squared is a squared, so therefore r is a. So based on that, your limits for r would be 0 to a, and your limits for theta would be 0 to 2 pi. Now we need the limits for z. Now look at what the problem says. The solid lies above the xy plane and is bounded by the paraboloid z equals x squared plus y squared. Alright? So if it's above the xy plane, note that z is always greater than or equal to 0. Okay? So your lower limit has to be 0. Now let's convert the z equals x squared plus y squared. What does that convert to? Z equals r squared. And so your limits for z would be 0 to r squared. So this would make the question a lot easier. So now let's set up the integral in cylindrical coordinates. So put your triple integral. Let's set up the integrand. What is the integrand going to be? 1, is it only 1? Times r, okay? So it's r dz dr d theta. 0 to 2 pi, 0 to a, 0 to r squared. Okay, let's work this out. Integrate with respect to z. 0 to 2 pi, 0 to a, rz, z goes from 0 to r squared, dr d theta. Substitute 0 to 2 pi, 0 to a. This just becomes r cubed, dr d theta. Integrate further with respect to r now. 0 to 2 pi, r to the 4th over 4, and r goes from 0 to r equals a d theta. Substitute 0 to 2 pi, you're left with a to the 4th over 4 d theta. And so your final answer would be a to the 4th over 4 times 2 pi, which is equal to pi over 2 a to the 4th. Okay, any questions? Let's look at this one. This one is a little tricky. Same thing for the volume enclosed by the hemisphere. X squared plus y squared plus z squared equals 4 for z greater than or equal to 0. And the cylinder x minus 1 all squared plus y squared equals 1. So again, you see there's over a cylinder, you need to use cylindrical coordinates, okay? So let's write the volume again, put down the formula so that you would know what to do. And then you are going to use cylindrical coordinates. So again, let us use the cylinder to find the r and theta limits. So let's write down this, and then what I would do, I would simplify this before I substitute the r cosine theta and r sine theta, okay? So let's FOIL this out. This becomes x squared minus 2x plus 1 plus y squared equals 1, which gives you x squared plus y squared minus 2x equals 0. Okay? That's what you get. Now you are ready to do the substitution. So x squared plus y squared is r squared, and this is a minus 2r cosine theta, which is 0. Now we can divide by r because r cannot be 0, okay? So we get that r equals 2 cosine theta. So this is the circle that we are looking at. Now I don't know if you remember some time ago we looked at a circle like this. Let me see if you can remember. First of all, what are the R limits? 0 to what? 0 to 2. All right? Remember what I told you? If you have an equation R equals A sine theta or R equals A cosine theta, the radius is A. Okay? Now let me see if you remember. What are the theta limits? What did I tell you about that? Do you remember? 0 to pi. Remember that? These type of circles, let's draw it again. Because if you put 0 to 2 pi, you go around the circle twice. Let me refresh your memory. Remember that? You want me to draw the table again to show you? That's okay? Exactly. Okay? So it's 0 to pi. So be careful with these circles. Alright? When they're written in that form. Okay, so we're good for that. Now we're ready for the z limit. So we know the lower limit for the z is going to be 0. Because they told you z is greater than or equal to 0. Now to find the z limit, therefore, we need to look at this hemisphere. Alright? Plus z squared equals 4. And we need to solve this for z. So r squared plus z squared equals 4. This implies that z squared is 4 minus r squared. And so z is equal to the square root of 4 minus r squared. Only the positive square root, of course. By the way, if this was a double integral, what we just found there would be your integrand. Okay? But now, because we're using a triple integral, it is going to be a limit. Okay, so let me say it again. If this question, you could have worked this question as a double integral. So let's say I gave you this question on an exam, just like that, and I don't tell you use triple integration or use double integration. You are free to use what you want. So in double integration, you would have these limits of the r and theta, but you'd be integrating square root of 4 minus r squared times r. Okay? But we're not going to do double integration. We're in triple integral, so let's do it that way. So let's set up. Okay, what is your integrand going to be? No, before we do that, let's okay, tell me what your integrand is going to be. R dz dr d theta. So z goes from 0 to square root of 4 minus r squared. R goes from 0 to 2. Theta 0 to pi. Okay, let's integrate. 0 to pi, 0 to 2. With respect to z, this becomes rz dr d theta. Put your limits. Z goes from 0 to square root of 4 minus r squared. This becomes 0 to pi, 0 to 2, r times square root of 4 minus r squared dr d theta. So you see it has become a double integral. So this is what I was telling you a while ago. If you had to do it just with double integration, you would just set it up that way. And as you can see, it's going to be shorter for you. Okay, instead of writing these things before. Okay, let's do this. What are we going to use here? Substitution. All right. So here, we're doing this substitution. Okay? We hope I have enough space here. So u equals what? 4 minus r squared. Du equals minus 2r dr. R dr is minus du over 2. Change the limits. R is 0 implies that u is 4. R is 2 implies that u is 0. So this becomes, leave your 0 to pi, then this becomes 4 to 0 minus, what do I have here? Minus, well, the square root thing becomes u to the half, but the RDR is du over 2, so you need a half du d theta. Any questions here? Okay, let's integrate. So 0 to pi. Okay, so the exponent is u to the 3/2. We are multiplying negative a half by 2/3, which becomes negative 1/3. Limits go from u equals 4 to u equals 0 d theta. Okay, let's substitute 0 to pi. So when you put 0, you get 0 minus minus. So that is 1/3 times, okay, let's do this slowly, 4 to the 3/2 d theta. Okay, what is 4 to the 3/2? That's 8. So that's 8 over 3, and then you have a pi. 8/3 pi, that's the solution. And you have calculators. When you do these things for homework or exams, always check your answer. You can put in a triple integral into your calculator. Okay? So you can check whether you are on the right track. Is it your turn? Take it away. Do it when you have set up the integral. Tell me what you have, just to make sure we are all on the right track. Okay, so let me check what you have, what you've set up. Okay, so it lies inside the cylinder. Can you give me your R limits? 0 to 4. Good. Your theta limits? 0 to what? 2 pi. And then what are your Z limits? They're very obvious there. -5 to 4. Okay. So this triple integral, the square root of x squared plus y squared dv, becomes, what does your integrand become? R squared. Good. dz, dr, d theta. Good. You're on the right track, so you can continue. Let's work that out. So this is 0 to 2 pi, 0 to 4, r squared z. Z goes from -5 to 4, dr d theta, which is equal to 0 to 2 pi, 0 to 4, 4r squared plus 5r squared dr d theta, 0 to 2 pi, 0 to 4, 9r squared dr d theta. Integrate 0 to 2 pi, 3r cubed, and r goes from 0 to 4 d theta. When you substitute 4, what did you get?
192.
What's that?
192.
And did you multiply by 3 too?
Yeah.
So when you multiply by 3, what did you get?
192.
Oh, 192. So 192 times 2 pi. Final answer is what? 384 pi. Nice. Sweet. We are moving on to spherical coordinates. So this one is going to be quite new to you. When a triple integral involves all or a portion of a sphere centered at the origin or a portion of a cone, and this is the formula for a cone, z squared equals x squared plus y squared, and these denominators are constants. And do you remember the formula for a sphere, by the way? Let me just put it up there. What's the formula for a sphere? X squared, AA. What's the formula for a sphere, anybody? You forgot that? Exactly. X squared plus y squared plus z squared equals to some constant squared. That's the formula for a sphere, right? Now don't tell me you forgot that. So if you see the triple integral involving something to do with a sphere or cone, converting the integral to spherical coordinates would be easier. Right? Spherical coordinates are useful in problems involving spheres and cones because the spherical coordinate equations are relatively simple, and this will make your integral very easy, okay, to integrate. So what are spherical coordinates? Let's look at the spherical coordinates. Let P be a point in space, so I'm going to show you how you define any point P using spherical coordinates. Rho, remember this is the Greek letter rho, is the distance from the origin to the point P. Theta is the angle between the positive x-axis and the projection of P onto the xy plane. Actually, maybe you should note that theta is similar to the theta in cylindrical coordinates. Okay? So it's similar to it. So whatever you used to do for cylindrical coordinates, that's what you do to find the theta. Okay? And phi, it's either phi or phi. So let's just say phi. Some people say phi. This is the Greek letter. This here is phi. Phi, phi, four form? Nope, it's phi. The angle is the angle between the positive z-axis and the line segment 0p. And phi must lie between 0 and pi because it is the angle between the positive z-axis, okay? So it does not go over pi. And so the spherical coordinates are in the form rho, theta, phi. And I'll draw a diagram in a little while underneath there. I just want to, I didn't leave space for a diagram. I'll draw it on the side. It's easy. It's not too bad. So this is what a diagram would look like. This is your Z. This is your Y. I don't want this below there. I'm going, oh my, let's do this again. One more time. Okay. Z, Y, X. All right. This is your origin. So let us say this is your point P. Okay. So let's start with rho. Rho is the distance from the origin. So this says, let me put that in blue. This distance is rho. Okay. Then theta is the angle between the positive x-axis. So no, let's do phi first. The angle between the positive z-axis and OP. This is phi. And then theta is the angle between the positive x-axis and the projection of B onto the xy plane. So let's project it. Let me use a finer point. So project P onto the xy plane. Okay. Let me put it in red. So that's the projection. Okay. And so this angle is going to be your theta. So make a note that this theta is the same theta as in cylindrical coordinates, okay? Now these are the formulas that you are going to use to convert. Alright, to convert integrals, to convert from rectangular to spherical and vice versa, these are the formulas. Very, very, very important. Encircle them, highlight them, you need them. X equals rho sine phi cosine theta, y equals rho sine phi sine theta, z equals rho cosine phi, and rho is the square root of x squared plus y squared plus z squared. Or basically rho squared is x squared plus y squared plus z squared. Alright, let's do some conversions. So these are the spherical coordinates. So remember the first one, and don't confuse, this one is rho, this one is theta, this one is phi. Okay? So we want to convert this to rectangular coordinates. So we are just going to use these formulas above there and find what x, y, and z are. So the first one, I'm not going to write them down again because they're right on the screen. X equals rho, which is 4 sine phi pi over 6 cosine theta cosine pi over 4. Work that out, you get square root 2. Y equals 4 sine phi pi over 6 sine theta pi over 4. This is again square root 2. Z equals rho 4 cosine phi cosine pi over 6, which is 2 square root 3. And so in rectangular coordinates, we get square root 2, square root 2, 2 square root 3. Done. Okay? Okay, next one. I think we're going to convert now from rectangular to spherical coordinates. Okay? So again, use the x and the y to find your theta. Okay? So let me just write this. X is 1, y is minus 1, z is minus square root 2. Let's find rho first. So rho is the square root of 1 plus 1 and z squared plus 2, which is equal to 2. Now we're going to use the x and the y to find theta, just as in polar coordinates. Alright, so draw your axes. 1, negative 1 here. This is the point, so it's as if we're projecting the xy plane, right? Okay? We want this angle. What is that? 7 pi over 4, correct? Right? Okay. Now we need phi, right? Phi is quite easy to find. You don't have to do any drawing. Just use the formula that z equals rho cosine phi. Just use that. Okay? And then just plug this in. So you have minus square root 2 equals 2 cosine phi. So cosine phi is minus square root 2 over 2, which works out to be 3 pi over 4. Okay? And so your spherical coordinates would be 2, 7 pi over 4, and 3 pi over 4. Done. Okay. Any questions? Now we're going to do some problems. So first of all, let us see how you convert to spherical. So you do the same thing. Using your formulas, change your x, y, and z to rho, theta, and phi. But you need to multiply by the Jacobian. Again, this here is the Jacobian for spherical coordinates, rho squared sine phi. And again, I want to remind you that in the next lecture, I think it's going to be the next lecture, I'm going to show you how you find the Jacobian. Okay, and why you need to always multiply by that whenever you are changing variables. Okay? All right. Number 1. Calculate the volume enclosed by the sphere x squared plus y squared plus z squared equals a squared. Now, as long as you see something like that, I would use spherical coordinates because it's a sphere. Okay? Now, you may tell me, I think you can also do it in cylindrical, you know, it wouldn't be too bad. You can also do it in polar as a double integral. It wouldn't be bad. Okay? But let's do it in spherical, all right? So we need rho, theta, and phi. Okay. So from x squared plus y squared plus z squared equals a squared, we need to do some substitutions. Let's convert this. So based on the formulas, rho, this is rho squared. What is on the left? So rho squared is a squared. So rho is a, right? So this tells you that rho goes from 0 to a. Now, it's an entire sphere, so theta would go from 0 to 2 pi, and phi goes from 0 to pi. Now, by the way, you're finding the volume of a sphere. So if you remember the formula for the volume of a sphere, you can check your answer. What is the formula for the volume of a sphere? 4/3 pi r cubed. Good. In this case, your sphere has radius a, right? So you should get 4/3 pi a cubed. So let's see that we get it. Okay, so remember, volume is equal to the triple integral of dv. Okay? Convert. So put your triple integral of 1, but you need to multiply by the Jacobian, rho squared sine phi d rho d phi d theta. Rho goes from 0 to a. It doesn't matter. What did I give you? I'll put what I gave you. What do you have? D theta d phi. Let's just put it. It doesn't matter because the limits are all constants. D theta d phi. So theta goes from 0 to 2 pi, phi 0 to pi. Okay. Okay, let's go. Integrate with respect to rho. 0 to pi, 0 to 2 pi, rho cubed over 3 sine phi from rho equals 0 to a d theta d phi. Substitute 0 to pi, 0 to 2 pi, a cubed over 3 sine phi d theta d phi. I hope this is not going to be tricky if I do this with respect to theta. It shouldn't matter. Integrate with respect to theta. A cubed over 3 sine phi times theta from theta equals 0 to 2 pi d phi. Substitute 2 pi, 0 to pi, a cubed over 3 sine phi, 2 pi, I forgot that. So that's 2 pi d phi. Integrate with respect to phi. You have a minus 2 pi a cubed over 3 cosine phi from 0 to pi. Substitute. Cosine pi is negative 1, so this becomes just 2 pi over 3 a cubed minus, that's a plus. Cosine 0 is 0, so that cosine 0 is 1, I'm sorry. So that's 2 pi over 3 a cubed, which works out to be 4 pi over 3 a cubed. Exactly what we were looking for. Okay. Any questions? Number 2. Evaluate this, where B is the ball. Ball, sphere, same thing. With center, the origin, and radius 5. Let me see if you can set up this integral and then we'll work it out. So set it up and then let's talk about it. Let's see what you have. What did you have for the limits for rho? 0 to 5. Limits for theta, 0 to 2 pi. Limits for phi, 0 to pi. So let's set up this integral. X squared plus y squared plus z squared squared dv. Okay. Triple. What does the integrand become? This is a squared. Very good. So this in the parentheses, there's rho squared, right? Rho squared squared. Let me just write it so you can see. But we need to multiply by rho squared sine phi, right? D rho, what did I put next? D theta? D phi. So 0 to pi, 0 to 2 pi, 0 to pi. So let's simplify that. Rho to the 6 sine phi d rho d theta d phi. Okay, now let's integrate. With respect to rho, let's do it. That's rho to the 7th over 7 sine phi. Woo! Ay, ay, ay. My word. I'm just gonna leave it as 5 to the 7th if you don't mind, okay? Rho equals 0 to 5 d theta d phi. 0 to pi, 0 to 2 pi. Can I put it outside? Let's get it out of the way. 5 to the 7th over 7. Sine phi d theta d phi, which is equal to 5 to the 7th over 7, 0 to pi. With respect to theta, so that's theta times sine phi, from theta is 0 to 2 pi. Very interesting. What do you see? Oh, no, sorry. Not interesting yet. Forget I said that. I recall that statement. Okay, multiply by 2 pi. Okay, I'm going to shift. Let me leave that there. 0 to pi, that is 2 pi sine phi d phi. Integrate 5 to the 7th over 7. This is minus 2 pi cosine phi from 0 to pi, which is 5/7 over 7 times, okay, what do we have here? Cosine pi is -1, so that's 2 pi, minus, so that's a plus 2 pi again, which is 4 pi. So that is 5 to the 7th over 7 times 4 pi. Are we good? You not good? You good? Okay. We're going to do some more, you know. Pardon me?
There's a lecture used to end right here.
Used to?
Yeah, now we have 2 more.
I wanted to give you some more problems, so I added 2.
Thank you.
You're very welcome. Okay. Let's continue. I will not say what I read in that remark. Let's go. Isn't that a lovely question? Just look at that. Just imagine I have given you this to evaluate, and I don't tell you use spherical coordinates. Yeah? Now you look at this and you say, this is crazy. Right? But you know, you can easily do that in cylindrical coordinates too. Okay, because as you can see, part of this looks like a circle. Look at the first 2 integrals, right? But because of the presence of the square root of x squared plus y squared plus z squared, I'm going to use spherical coordinates. It will be easier to convert. Okay? So let's do this. What I will do, first of all, is to take those, the same thing that we did before. Take the first 2 integrals, draw the picture so that you can find what theta is. Remember what I said? Theta is the same as in cylindrical coordinates. So just draw the picture and tell me what you get. What did you get? Circle. Okay. So remember we're not looking at r, right? It's theta we want. What is theta? 0 to 2 pi. Now phi also goes from 0 to pi. Alright, there was no restriction there, so we're good. Sweet. Now, what is z? Although it's kind of obvious, what is the radius of this circle? It's 1. So, not z, I meant to say rho. Rho goes from 0 to 1. Beautiful. Okay? Are we ready to convert? Let's do it. Let's get the integrand set up. What is x squared plus y squared plus z squared? Rho squared. So the square root is just rho multiplied by rho squared sine phi d rho d theta d phi. 0 to 1, 0 to 2 pi, 0 to pi. Okay, let's work this out. First of all, let's simplify that. That's 0 to pi, 0 to 2 pi, 0 to 1, rho cube sine phi d rho d theta d phi. Integrate with respect to rho. So that is rho to the 4th over 4 sine phi. Rho goes from 0 to 1 d theta d phi. Substitute 0 to pi, 0 to 2 pi, 1/4 sine phi d theta d phi. Any questions before I continue? Okay. Integrate with respect to theta. 0 to pi. I'm going to put 1/4 theta sine phi from 0 to 2 pi d phi. Zero to pi, substitute 2 pi in there. What do we get here? Pi over 2 sine phi d phi. Integrate minus pi over 2 cosine phi 0 to pi, which works out to be pi over 2 plus pi over 2, which is pi. So the integrals are not too bad to evaluate, because more or less you realize we're doing the same thing. Any questions before we do the last one? One for the road. Yeah? Let's do it. That's what we say in the Caribbean. One for the road.
Sounds unsafe.
It's what?
Don't talk about math that way.
That's a red solo count for me.
Okay, let's go. Use sphericals. Now, I said to set this up, do not evaluate. Why did I say so? Because I think we would have been doing the same kind of integral. Okay? So we're just going to set it up. And the reason I say set up, because this is a wicked one. Okay? So we're going to start with the easier part to draw. Good? So take the first two integrals and draw what you think this is going to look like. So draw it and then you tell me. This here. Are you sure it's a semicircle? It's a quarter, isn't it? Because x just goes from 0 to 3. Yeah? So we only want this. Good? So right away, we have found theta. What are our limits for theta? 0 to pi over 2. Okay. So we are done with the first two. Let us look at the last. Did I put a minus there? Where did this minus come from? I think this is a little an error here. I don't need a minus there. You don't need a minus, okay? Because I want this to be a cone. Okay, so the z limits, let's write them down. We have z equals square root of x squared plus y squared. This is a cone. And then we have z equals square root of 18 minus x squared minus y squared. Now, if we deal with this thing on the left, it's not going to get us anywhere with our, because what we want to find is rho, right? This is not going to get us anywhere. Good? But so let's try the one on the right. When you square both sides, you get that z squared is 18 minus x squared minus y squared. So, x squared plus y squared plus z squared equals 18. As you can see, we are getting somewhere. Let's find our rho. Rho squared is 18. So rho is square root 18. And if you want to simplify that as a radical, that's 3 square root 2. You don't have to. It just looks nice. So rho goes from 0 to 3 square root 2. Good. We have our rho, we have our theta, we need to find our phi. So that is where you need to really concentrate for that. To find phi, you need to use that last formula that I gave you, okay? So to find phi, use the fact that z is rho cosine phi. I gave you that. Good? We have rho, which is 3 square root 2, but we do not have z. Okay? So what you need to do, if you look at the question again, we need to take these two z's and solve them simultaneously. So that's what we need to do. So to find z, solve z equals square root of x squared plus y squared, and I will just take the x squared plus y squared plus z squared equals 18. Okay, because it means the same thing. So we need to solve these two. So z equals square root of x squared plus y squared implies that z squared is x squared plus y squared, right? Remember, we're solving simultaneously. So the best thing to do is to solve this by substitution. So take this and substitute into the other equation. So substitute, we get z squared plus z squared is 18. 2z squared is 18. Z squared is 9. So z is 3. So now we can use the formula. So z equals rho cosine phi tells us that 3 equals 3 square root 2 cosine phi. So 1 over square root 2 is cosine phi, and so phi is pi over 4. So therefore the limits for phi, 0 to pi over 4. Okay? Ready? Let's set up, let's convert. Triple integral, we put the limits last. The integrand is x squared plus y squared plus z squared, which is what? Rho squared. What do we need to do? Multiply by the Jacobian. Rho squared sine phi d rho d theta d phi. So 0 to 3 square root 2, 0 to pi over 2, 0 to pi over 4, and just simplify that. And this part just works out to be rho to the 4th sine phi. Questions? Somebody has a question.
Is it a coincidence that when theta equals, when theta equals 2 pi, phi equals half?
I knew I was going to get that question. That you wonder if it's a coincidence that phi always seems to be a half of it. No. Yeah. Yes, it's a coincidence. Sorry. Sometimes it doesn't happen that way. Okay?